we discussed energy stored in the capacitor when charged. If the capacitor already carries charge Q and we want to add that Q of charge on top of Q to the capacitor, how much work do we need to do to add that Q of charge? So in other words, what the work we done would be transferred to the energy stored in the capacitor. Q times delta V, which is to give us the energy. So delta Q times this delta V for this blue rectangular area will tell us what would be the energy required for us to transfer delta Q of charge on top of the Q charge already stored in the capacitor. Which means if we add the area of all those rectangles together, it will give us the energy stored in the capacitor when carrying charge Q. The area of this triangle is given by 1/2 base times height, and the base is Q, height is delta V. So the energy of a capacitor carrying charge Q with potential difference delta V is 1/2 Q delta V. Q equals C delta V. If we replace Q by C delta V, we also have energy equals 1/2 C delta V squared. Similarly, delta V equals Q over C. So if we replace delta V by Q over C, we will get the energy stored in the capacitor also equals to 1/2 Q squared over C. So there are three quantities for a capacitor: capacitance, charge, and delta V, potential difference. Because C equals Q over delta V, so only two of those three quantities are independent. If those two are already fixed, then the third one is fixed. So we only know two of those three quantities to calculate the energy of the capacitor. So in the problem, it depends on which two quantities are given. You are then using those two given quantities to calculate the energy of the capacitor carrying charge Q with potential delta V. One of the applications of capacitor that saves a lot of lives is defibrillator.
Your heart beats an estimated 3 billion times during your lifetime. But when a heart attack strikes, you wonder, will this be my last? Defibrillators send an electric charge through an erratically twitching heart, shocking it back into rhythm through electrodes placed on the chest. These life-saving machines rely on a capacitor, a device that stores electrical energy. It consists of two parallel metal plates separated by non-conducting material called a dielectric. In a defibrillator circuit, by closing the switch to position A, the capacitor will charge up to a voltage equal to the applied voltage. When shifted to position B, the capacitor rapidly discharges through the paddles to the person and helps get the heart beating normally. The charge on a capacitor is dependent on its capacitance and the applied voltage. In the case of standard defibrillators, this may be hundreds or thousands of volts. The capacitance of the capacitor depends on the size and the spacing of its plates. It takes energy to move charge onto a capacitor. The energy stored can be computed from, when applied to the heart, up to 360 joules of energy can be released into the person's body in 1/100th of a second. The use of a defibrillator within the first minute of collapse increases the survival rate to nearly 90%. These devices can clearly turn a bad day into the best day of your life.